I've had another dream. This dream is about faster than light communication. Impossible. Imagine both of us here together on Earth. I'm going to take a journey. Before I leave on my journey, here on Earth, we pass a laser through beta barium borate crystal and create an entangled photon pair. One of those photon pair streams will come with me on my journey. One of those photon pair streams will stay with you. The photons that I have and that you have are entangled and in a state of superposition regarding their axis of polarization. When I've completed my journey far, far away, I will begin to measure the axis of polarization of my photons. There is nothing you can do back on Earth that will alter the random state of the axis of polarization that I measure far, far away. There is no signal, no communication that can be sent through the axis of polarization. How then do we send a message? Far away, as I measure these photons, I will detect very small differences in the amount of energy certain photons possess. The order of magnitude of this energy differential will be extremely small, on the order of 1 times 10 to the negative 26 joules. Why do I measure a difference in the photon energy? Because back on Earth, you have chosen to measure the photons' axis of polarization either before or after I have measured the axis of polarization. If you measure the axis of polarization before me, you have driven down the entropy, the information entropy of the pair to 0 regarding the axis of polarization. There is 100% certainty that whatever axis of polarization you measure, I will measure the same. The entropy of my entangled photon becomes 0 if you have already measured the pair. But as I said, there is no change in the random axis of polarization. If you choose to measure the photon that you possess after I have measured mine, I will detect a higher energy of my photon, a very small increment higher energy, on the order of 1 times 10 to the negative 26 joules. This is the way the signal is sent. I'm going to get right to this. This is the Shannon-Landauer faster than light communication protocol. This is the experiment setup. You begin with a laser emitting light at 405 nanometers. Shine it through a beta barium borate crystal. Out of that crystal exits 2 photon streams at 810 nanometers. Each stream is entangled with the other and in a state of superposition regarding its axis of polarization. These are the symbols. This is a reflective linear polarizer. This is a single photon in a state of superposition regarding its axis of polarization. This is a single photon with its axis of polarization determined.
in a collapsed state. We're going to manipulate this arm to receive a signal on this arm. The signal on this arm will always be received at time 2. We will always measure at time 2. And on this arm, we will measure at either time 1 or time 3, varying the time at which we measure either before or after time 2 is how we create a signal that is received at time 2. How do we do that? Well, exiting the laser, we have a photon pair that is in a state of superposition and entangled with regards to its axis of polarization. If we choose to measure on this arm at time 1, we collapse, we determine the state of this photon in a state that is in a state of superposition, and we get a measured result. By determining the axis of polarization on this arm, the entangled pair has its axis of polarization determined regardless of space-time separation. This is a fact of quantum mechanics. So then, striking the reflective linear polarizer at time 2 on that arm, we have a determined photon that strikes that polarizer. Now, alternatively, if we measure at time 3, what is going to strike the reflective linear polarizer on the receiving arm is a photon in a state of superposition that will collapse this side. It will collapse this side, which we don't really care about because this is the signal that we're trying to receive. So what I'm telling you is the signal is whether this reflective linear polarizer encounters, measures, collapses, determines a photon which is in a state of superposition versus a photon which has its axis of polarization determined. The signal will be a very, very small quantity of heat which is generated and deposited in this measuring device. I want to explain just a little bit more about quantum mechanics. A photon which is in a state of superposition embodies more information than a photon which has been determined. We call this transition collapse, and in collapse, information is essentially lost. It is leaked into the environment in the form of heat. This is an irreversible reaction, meaning the amount of information present in a photon which has had its state collapsed into a determined measurement cannot be used to accurately recreate, or to recreate, period, the photon that was in a state of superposition which led to that photon. This is an irreversible reaction that goes one way. You cannot reverse it. The Landauer principle is generally accepted and taken to be a restatement of the second law of thermodynamics, which is, in Landauer's words, that any irreversible calculation entails heat, the generation of heat in performing that calculation. I've just said this is an irreversible calculation, therefore heat must be released by this. Let me restate this in a simpler form. Simply, I am saying this reaction does not equal this reaction. There is a difference. In order to make these equivalent, we need to add a term on this side. Now, each side of this equation is equivalent. The interaction of a photon that is an entangled state causes more heat to be deposited on the measuring device than the interaction of a photon which is already in a collapsed determined state and its interaction with the measuring device. And by alternating the interaction as either collapsed or in a state of superposition, you alternate how much heat is deposited in your measuring device, and that is your signal.